Hello everyone, welcome back to the video lecture series for EC302 Digital Communications. In this video, we shall discuss about the orthogonal frequency division multiplexing, or in short OFDM. The video covers the following important topics: the introduction to multi-carrier communications, the concept of OFDM, the modulation and demodulation shown through the block diagram, and also the advantages, the shortcomings, and the applications. Now, before we start with OFDM, let's look at what is multi-carrier modulation. The initial development of multi-carrier communication system was basically done by military systems around the late 1950s and middle of 1960s. So these systems which were developed are called classical multi-carrier modulation systems, or MCMs, and they transmitted data on non-overlapped band-limited orthogonal signals. Now the initial, or the one which was developed earlier, such systems required analog oscillator and filters of much wider bandwidth and very sharp cutoff. So, due to this reason, the concept of OFDM has not gained much importance since then. So much attention of popularity was not gained that time because of the difficulty in subcarrier recovery. That is, recovering the signals at the receiver was not that easy due to the complexity in the circuit and the sharp filter designing and all that. Later on, with the development of the IDFT and DFT, that is discrete Fourier transform techniques, and employing those techniques in OFDM, it was possible to eliminate this use of subcarrier oscillators at the transmitter and the receiver. So the availability of fast DFT algorithms, which is nothing but the FFT, fast Fourier transform, significantly reduced the implementation complexity of OFDM modems. And then further studies and further development led to the advancement in the integration of such technology, much more cost effective. So all this was done to accommodate more number of users or to meet the higher demand for traffic. So, and of course, if we look forward, the next generation wireless communications would require higher data rates for transmission to meet the ever growing demand of quality services. To meet the growing demand, we incorporated the multi-carrier transmission techniques. Now, orthogonal frequency division multiplexing would serve as a future promise to meet up the high demand of traffic. Now, this multi-carrier modulation compared to the single carrier modulation, what is the major difference? Or, as I told you, it eliminates the need of these sharp filters. And if you look at this figure over here, to the left, you can see the single carrier modulation diagram, and to the right it is multiple carrier modulation scheme. So in single carrier modulation, as the name says, there's only single carrier signal to transmit the data, and whereas in a multi-carrier modulation you can see that there are multiple carrier signals, and on top of which the data is being split and modulated. So rather than a single carrier, we have multiple carriers in multiple carrier modulation scheme. What could be the advantage of going for multiple carriers rather than a single carrier? See, if in a single carrier communication, what happens is you modulate the message or superimpose the message onto the carrier and you transmit it, right? So as the signal is propagated through space, it may undergo different um, fading effects or different disturbances or interference, which may lead to deep signal fading or loss in the strength of the signal, or the message may get completely distorted. In such a scenario, to overcome the problem of symbol interference and fading, we introduce this concept of multiple carrier modulation, where you use many carriers to transmit the message. That is, the message is being split into smaller parts and then it is superimposed onto many subcarriers, and then it is clapped and transmitted. So this multi-carrier modulation technique was considered to be more efficient in case of its spectrum and the removal of intersymbol interference and intercarrier uh, interference, and also the use of very complicated filters were also eliminated. Now, one such technique of multi-carrier modulation scheme is OFDM, or orthogonal frequency division multiplexing. Now, the basic principle of this multi-carrier communication, you might wonder, how are you actually transmitting many such carriers all together or at once? Don't they interfere with each other? To avoid the interference of all these subcarriers with each other, there's a principle being applied which is called orthogonality. Now, what is orthogonality? So, orthogonality means, or two signals are said to be orthogonal if they are mutually independent of each other, or if two signals have this property of orthogonality, they can be transmitted successfully or perfectly over a single or a common channel without being interfered. In mathematical terms, the principle of orthogonality says that the two signals are said to be orthogonal if the product of their functions, when integrated over one symbol period, is results in 0. That is when two signals are said to be orthogonal. That is, integral of the two functions over a symbol period results in 0. That is when we call the two signals to be orthogonal, or they don't interfere with each other as long as this principle is met. Now, the same principle of OFDM the same principle of orthogonality is being applied in OFDM as well. And the basic principle of OFDM is to split a high data rate stream into a number of lower data rate streams and then transmit these streams in parallel using several orthogonal subcarriers. That is basically parallel communication. So it is a form of multi-carrier modulation technique, and it divides the high data rate stream into a number of lower data rate stream, and they're sub sorry transmitted simultaneously over number of subcarriers. And these carriers have to meet the property of orthogonality. Now, OFDM is can be considered as, or the frequency division multiplexing technique, which I've already learned before, can be considered to be the mother of OFDM, because it is from this frequency division multiplexing technique that this OFDM technique was developed. Benefits is it can fight the adverse effects of multipath propagation. So all the drawbacks of multipath propagation can be mitigated or avoided or overcome using this OFDM concept. This is how the spectra of OFDM looks like. The figure A shows the single subcarrier spectrum, and this figure B shows all the subcarriers overlapping with each other, but they don't interfere and they remain orthogonal. When do you say they are orthogonal? Look at the figure and you can see the carrier centers, that is peak, one carrier peak falls at the null frequency of the other. That is zero crossing. So the peak of one subcarrier falls at the null of the other subcarrier. That is when we say it is orthogonal. Or you can say that peak of each signal coincides with the trough of the other signal. and the subcarriers are spaced at 1 by Ts to meet the orthogonality principle. Further, moving on to the generation and detection of OFDM signal, let's have a look at the block diagram here. And you can see the main components or the main blocks over here are, the first one is the modulator. Then you have the serial to parallel, S bar P is nothing but serial to parallel converter. And then you have the IFFT, inverse Fourier fast Fourier transform, and you have the parallel to serial conversion, and there's something called cyclic prefix addition and the DAC, and the signal is transmitted. Whereas, and then the signal is transmitted through the channel, and at the bottom figure is nothing but the receiver, where after receiving it there's an ADC over there, and then the cyclic prefix which was added at the transmitter has been removed. Then you have the opposite of parallel to serial on top, you have the serial to parallel converter, then FFT at the demodulator, parallel to serial converter again, and then the demodulator, and you get back the bit stream or the data. Now here let's look at each block in detail. The first one is a modulator. Now here you can see the input is a serial data stream. Now the modulation is done to convert the input data stream into a multi-level data stream. That is, the binary data will be transformed into a multi-level signal, reducing the symbol rate. Now you have different modulation types available, as we know: BPSK, QPSK, QAM. It could be 16 QAM, 64 QAM, or even 256 QAM. The data allocated to each symbol depends on the modulation scheme being used and the number of subcarriers. Next, after modulation, you have the serial to parallel conversion, where the data, whichever is coming in the serial form, is input into the parallel form. Okay. A serial to parallel conversion stage is needed to convert the input serial bit stream to the data to be transmitted in each OFDM symbol. If you convert the serial data to parallel, then the data rate gets further reduced by factor n. Next is the IFFT block, that is inverse fast Fourier transform. The parallel data after serial to parallel conversion, the data is being fed to the IFFT. So the parallel data stream is then subject to IFFT, and then they are summed up. This constitutes the OFDM modulation. IFFT converts the signal from frequency domain to time domain. The time duration of the IFFT time signal can be calculated by multiplying the number of bits by the sample period. Now, it converts, basically IFFT is done. Usually we see IFFT at the demodulation, right? And FFT at the modulation. But in OFDM, first we perform IFFT. The reason is the signal has to be converted from the frequency domain to the time domain so that it can be transmitted through the channel. So next is the data after it's been converted to the time domain. It goes through a parallel to serial conversion again, because data is transmitted through the channel, has to be transmitted through the channel, and before transmission what is performed is there's something called cyclic prefix. Okay, that is nothing but a guard interval which is used to suppress the intersymbol interference caused by multipath distortion. Now, prior to the transmission, we add some guard interval or some cyclic, we call it cyclic prefix, CP, and the cyclic prefix is nothing but the last part. We have an OFDM symbol, and so what we do is the last part of the OFDM symbol is being copied over to the beginning of the OFDM symbol. Okay, so instead of leaving the guard band to be blank, what we do is, to have the continuity over one symbol period, we copy the last part of the OFDM symbol to the front of it, and this portion which is being added, or the last portion which is taken to the front, is referred to as the cyclic prefix. Using the cyclic extended symbol, the samples required for performing the FFT can be taken anywhere over the length of the cyclic prefix. So basically this is done to overcome intersymbol interference. Next, and then it is converted into the analog form and then transmitted. At the channel, what happens is it is received and it's converted back to the digital form, and whatever the cyclic prefix was added to overcome intersimple interference has been removed, and then parallel and serial to parallel conversion, and the convert it is the signals are converted in parallel to perform FFT. And there's something called pilot symbols which are inserted as the reference symbol, reference carrier frequency symbols, and which are then parallel to serial converted, demodulated, and you get back the bit stream. So this is, and FFT again converts the received data from time domain back to the frequency domain. So this is it about the block diagram of or the generation and demodulation of OFDM. If you have a look at it in a closer perspective, you can see modulation could be QPSK or QAM or anything, and the signal after modulation would appear as shown in the figure in the frequency domain, and the frequency domain is signal is converted to the time domain signal by performing IFFT, and then the further blocks are being added up. So this is a closer picture of the signal for better understanding. And at the receiver, whatever you receive would appear like the time domain view after the interference and all that would seem to be like this, the red one. And then when after performing FFT, you'd get back the frequency domain view. So, as I told you, the cyclic prefix is added to remove or reduce intersymbol interference. So, what happens is you can see the delayed version of the symbol overlaps with the adjacent symbol. That is, intersymbol interference is nothing but if a signal is delayed, it interferes with the spectra of the other one and it causes intersymbol interference. So, one symbol solution to avoid intersymbol interference is to introduce the guard band or provide some interval between or a gap between one symbol and the other, so that even though it spreads out or delays, it will occupy the guard interval and not cross the boundary of the other signal. So guard interval or the guard band is essential to remove the intersymbol interference. So to avoid that or to provide that space to overcome this delay, that is referred to as a guard band, or to the guard band here is being inserted with a cyclic prefix, which is nothing but the last part of the OFDM signal is being taken to the front, is copied to the front. And the hardware does not allow blank space because it needs to send out signal continuously, so you cannot leave it blank because the hardware doesn't support it. So what we do is we add a cyclic prefix, or we copy the last or the tail of the OFDM signal and glue it up with the at the beginning in front. Now, what are the advantages of using this OFDM technique? So, it is immune to selective fading, and it reduces interference. The spelling mistake, I'm sorry. OFDM improves spectral efficiency, and not just the channel interferences but also the intersymbol interferences, and equalization. Without the previous one in single carrier modulation, we had to go for a complex equalization technique, whereas here since we are using low or narrow band signals, the high band signal is being split into the narrow band signal, so the equalization process is made simpler, and you can use different modulation schemes as well over here depending on the channel characteristics, or studying the channel characteristics we can perform the or we can select one of the best modulation schemes being available. Okay, there are few disadvantages as well over here, that is a high peak to average power ratio. This improves the or this increases the complexity of the circuitry, and to provide this high peak to average power ratio, so the amplifiers and all the uh, receiver and circuitry has to be complex to design or to detect the signal correctly, and then it is sensitive to carrier offset and drift, that is always they have to remain orthogonal with each other. And if there's any offset, or if there's any drift or change or a shift in the signal, uh, the frequencies, then there would be a loss of data, as they no longer remain orthogonal. So and accurate time and frequency synchronization is also required over here to keep them in place. Now applications, if we look at in the present world, it's being used in the Wi-Fi wireless fidelity network in using it's 802.11a standard, 802.11n, 802.11c, and even more. And it's also being used in cellular telecommunication standards, the WiMAX technology, digital broadcasting, like broadcasting standards like DAB, DVB, digital video broadcasting, audio broadcasting. Now these are one no very the very few applications are being listed out here. There are much more applications under OFDM which are beyond the scope of discussion over here. So you can refer the or you can browse for the applications of OFDM, and you would get many or plenty of applications or plenty of areas where this OFDM has been used successfully. Thank you for watching the video. I hope the concept of OFDM is clear to you, where you actually the high data end stream is being split up into lower data streams and transmitted over sub different multiple subcarriers to reduce the multipath propagation drawbacks. All right. Thank you for watching the video.